Let's talk about divergence a little bit. Divergence of a vector field at a point sometimes called flux density. Suppose you have a vector field and it represents the velocity field. F of x and y is equal to m of x and y in the direction of x-axis plus n of x and y in the direction of y-axis is the velocity field. Of a fluid flow in plane and the first partial derivatives of m and n are both continuous. Suppose you take a point in the region R and let A be a small rectangle with one corner at x and y. Let's move this a little bit here so we can crack this. This is our point, x and y. And this is our rectangle A. Note that the sides of this rectangle are parallel to coordinate planes. X and Y axis. So if we want to work with these sides, let's just represent them by delta X and delta Y. Let me use a different color. Delta X and delta Y. So this point is X and Y. On the right-hand side, you're going to get X plus delta X and Y. The next point, it's going to be X and Y plus delta Y. And then finally, we have X plus delta X and Y plus delta y. So note that the rate at which fluid leaves the rectangle is approximately f of x and y dot negative j times delta x, which is nothing but negative n of x and y delta x. This is the scalar component of the velocity at x and y in the direction of outward normal times the length of the segment. Now let us just check the rate in the direction of each side. Exit rate for the top part, it's going to be f of x and y plus delta y. Which is just dot product with j. We have a vector field dot j delta x is equal to n of x and y plus delta y delta x, and for bottom you have your vector field x comma y dot product negative j delta x, which is negative n of x and y delta x, and then for the right part your vector field f of x plus delta x and y dot product with I delta x. Oh, sorry, this is going to be delta y, which is equal to m of x plus delta x and y times delta y. And finally, for the left-hand side, your vector field evaluated at x and y dot product with negative I and delta y, which is negative m of x and y delta y. So as you can see, you can combine the opposite pairs, and you're going to have the following combination. Move this a little bit here so we can see top and bottom. Let's use a different color. This guy gives you, so here you have the sum of n of x and y plus delta y, delta x minus n of x and y, delta x, if you combine these two, get approximately partial derivative of n with respect to y, delta y, delta x. Because there's a difference between n of x and y plus delta y, n of x and y, if you remember taking the partial derivative, this is nothing but the partial derivative of n with respect to y times delta y times delta x. And finally, if you combine left and right, what you're going to see, you're going to have the partial derivative of m with respect to x, delta y. So if you take these two and add them together, you're going to have the flux across a rectangle boundary. Partial derivative of n with respect to y, delta x, delta y, plus partial derivative of n with respect to x, delta y. The component delta x, delta y shows the rectangle area. It's an estimate. So if you do the division, the flux divided by the rectangle area gives you partial derivative of n with respect to y plus partial derivative of n with respect to x, which is nothing but the divergence. So you have the flux divided by delta x, delta y, which is the divergence of f, which can be written as partial derivative of n with respect to x plus partial derivative of n with respect to y.